What's up, fellas? Here's an upper-level ISEE quantitative comparison problem where we're given equilateral triangle PEN and square ENTA, and we have to compare the quantities of the area of triangle EAT right here and triangle PEN. So I'll give you guys a second to see if you can solve that on your own. All right, second's up. So what I want to do first is draw each shape individually so that we can compare them side by side. This diagram makes it just a little bit more confusing than it needs to be. So once I do that, we have triangle EAT and PEN. Notice EAT is a right triangle with this right angle that happens to be isosceles because EA and AT have the same length. They're congruent. Triangle PEN is equilateral, meaning all the sides have the same length and they're all congruent to each other. So now I want to notice that AT is the same as EN. These are congruent sides with the same length, so they have the same length base, each of these triangles. And that's going to be useful because the area of a triangle, you might know, is base times height divided by 2 for both of these triangles. So the difference, since they have the same base value, is going to be the height. Whichever one has a greater height will have the greater area. So the height is pretty easy to solve for EAT because we know it's the same as the base. And we can put it into this formula. I'm going to just let the base and the height both equal 2. And we get the area of this triangle is 2. Now, you might say I wrote this complicated formula here. You don't need to know this, but it's useful. The area of an equilateral triangle is one side, or S, squared times the square root of 3 divided by 4. If I do the same thing and plug in 2, then I get the area of this one is root 3. So you can clearly see EAT is a little bit larger. But let's say you didn't know the area of an equilateral triangle. That's kind of a unknown formula for lots of people. So what we can do instead is kind of visualize this equilateral triangle right here, where we can see this base is 2, and this height is going to be the dotted line right here. It needs to be perpendicular from the base, sticking straight up. And if we were to extend this side, which we know is the same as the height here, it's congruent to all these sides. If we were to extend this side and just kind of drag it up like that, it would be a little taller than the equilateral triangle currently is. And since the height would increase if we were to bring it up and make it a right triangle like this one, that means that the height EA is greater than the height of triangle PEN.